This is audio recording for visually impaired students. So let's start chemistry of noble gases from Pradeep publications. Group 18 of the periodic table consists of 6 elements: helium, neon, argon, krypton, xenon and radon. This is a unique group as all its members are gases at ordinary temperature and pressure. Prior to 1962, the elements of this group were known as inert or rare gases. Today, both the names have been proved wrong. This is because these gases are no more rare now as these are found in the atmosphere, although only argon is present in high proportion. Some of these gases, especially xenon and radon, have been found to be reactive and accordingly we can no longer call them as inert gases. These gases have been correctly named now as noble gases in view of their reluctance to react with everything. In fact, the noble gases make up least reactive group in periodic table. Position of noble gases in the periodic table. Mendeleev arranged all the known elements in the form of a table known as periodic table in 1869 on the basis of physical and chemical properties of the elements. The noble gases were not known at that time. As a result, no place could be allocated to these gases. Later on, when these gases were discovered and characterized, it was thought to position these gases in the periodic table on the basis of their physical and chemical properties. It is curious to note that these gases are not reactive at all on the basis of their atomic mass and non-reactive nature. Ramsay, the main inventor of these gases, proposed altogether a new group called zero group for these gases. The group 0 suggests extreme inactivity or zero valency, combining capacity of the noble gases. Prior to the discovery of noble gases, the elements happened to be arranged in a manner that all the electropositive elements were placed on the extreme left of the periodic table and the electronegative elements on the extreme right of the periodic table. Thus, one can sense a very sudden change in the periodic properties from the most electronegative halogen to the most electropositive alkali metals. Now, the inclusion of these gases in between the halogen and the alkali metal appears justified as these gases have neither electronegative nor electropositive character. The position of these gases was finally confirmed by Moseley, who suggested atomic number as the basis of classification of elements in modern periodic table. These gases now happily enjoy the last column on the extreme right of the long form of periodic table. The discovery of noble gases. Helium was detected for the first time in the spectrum of the Sun in 1868, hence its name derived from Greek helios for sun. It was nearly 30 years later when Ramsay found helium as a gas given off from a radioactive uranium source. The discovery of argon was made by Lord Rayleigh by measuring carefully the density of nitrogen samples from different sources. He observed that the nitrogen samples from air was always denser than the obtained from decomposition of ammonia. It is interesting to note that when Ramsay burnt magnesium in nitrogen from air, he found a small amount of the gas which was identical to that found by Rayleigh. He named this gas as argon. It comes from the Greek argos for the idle one. The other three gases were obtained by the fractional distillation of liquid air and were named neon, the new one, krypton, the hidden one, and xenon, the stranger. The name radon comes from its radioactivity. William Ramsay and Lord Rayleigh were the main contributors for the discovery of inert gases, and both of them were decorated with the Nobel Prizes 1904. Electronic configuration. The electronic configuration of the elements of noble gases is presented. Helium, symbol He, atomic number 2, electronic configuration 1s2. Element neon, symbol Ne, atomic number 10, electronic configuration 1s2, 2s2, 2p6. Argon, symbol Ar, atomic number 18, electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6. Krypton, symbol Kr, atomic number 36, electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6. Xenon, symbol Xc, atomic number 54, electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2 4p6 4d10 5s2 5p6. Radon, symbol Rn, atomic number 86. Electronic configuration 1s2 2s2 2p6 3s2 3p6 3d10 4s2 4p6 4d10 5s2 5p6 4f14 5d10 6x2 6p6. Helium, the first element of the noble gases, has the electronic configuration 1s2, whereas all the other elements have the general electronic configuration ns2 and p6, where n is the period number. Thus, all the noble gases, with the exception of helium, have high electrons in the valence shell. Physical properties. All the elements of noble gases are placed in group 18 of the periodic table. It is a unique group where all the members are colorless, odorless and monoatomic gases at room temperature. The monoatomic state of these gases is due to the stable electronic configuration of their atoms. All these gases occur in the atmosphere. It is interesting to note that total volume of the noble gases comes close to 1 by 1/20th of the volume of air. These gases neither burn nor spot combustion. In fact, these gases constitute the least reactive group in the periodic table. Atomic radii. The atomic radii of noble gases increase from helium to xenon as one moves from top to bottom in group. This is because on moving from one atom to another in a group, there is increase in the principal quantum number. As a result, new shells are being added and the electron cloud expands. The atoms of noble gases are held together by weak van der Waals forces. These forces are very weak. To give you an idea, let us consider the bond energy of a normal ionic or covalent bond compared to the bond energies in a system where van der Waals forces are operative. The bond energies in the former varies from 100 to 500 kJ per mole, whereas in the latter case where van der Waals forces are operative, it varies from 5 to 50 kJ per mole. The atoms of the noble gases are held together at longer distances. It is therefore important to mention that in case of noble gases, one should talk of van der Waals radii rather than covalent radii. This is because noble gases do not form covalent bonds but are held together by van der Waals forces. Number 2. Ionization energies. The first ionization energies of noble gases are very high. This is primarily because of the completely filled electronic configuration. However, within the group, the ionization energies decrease down the group from helium to radon because of the increase in atomic radii. Number 3. Electron affinities. The electron affinities of noble gases are nearly zero because of their stable electronic configuration. It clearly suggests that the noble gases have no tendency to accept electrons. Number 4. Melting and boiling points. The melting and boiling points of noble gases are very low. This is because the atoms of these elements are held together by weak van der Waals forces of attraction, both in the liquid as well as in the solid state. An inspection of the table reveals that down the group from helium to radon, the melting and boiling points of these elements show a regular increase due to corresponding increase in the magnitude of their van der Waals forces with the increase in the size of atom. Number 5. Solubility in water. The noble gases are slightly soluble in water. The solubility has been found to increase down the group from helium to radon. Number 6. Ease of liquefaction. The noble gases are not easily liquefied. The ease of liquefaction of a gas depends upon the magnitude of attractive forces present in the atoms or molecules. Since these gases are held together by weak van der Waals forces, this cannot be easily liquefied. However, as the atomic size increases, the magnitude of the van der Waals forces increases and thus the ease of liquefaction increases as one moves down the group from helium to radon. Chemical properties of noble gases. After the discovery of noble gases, many attempts were made to prepare compounds of these elements. However, all attempts before 1962 were unsuccessful and the elements were compelled to be known as inert gases. The inertness of these elements to chemical reactivity is attributed to: Number 1. The stable closed shell configuration. ns2 and p6 of all noble gases excepting helium, which has the electronic configuration of 1s2. Number 2. The high first ionization energy of noble gases. Number 3. Nearly zero electron affinities of noble gases. On the basis of above facts, noble gases do not have any tendency to lose gain or share electron with other atoms. The first compound of the noble gases were prepared by British-born Canadian chemist Neil Bartlett in 1962. In fact, Bartlett was studying the reactions of platinum fluoride, which is a red crystalline solid. He observed that when PtF6 is exposed to molecular oxygen, a yellow ionic solid of composition O2 positive, PtF6 negative is formed. The above reaction clearly demonstrates that O2 has been oxidized to O2 positive, thus suggesting the high oxidizing character of platinum fluoride. While teaching a first-year chemistry class, Bartlett noticed that the first ionization energy of xenon gas is 1170 kJ per mole was almost identical to that of dioxygen molecule, that is 1175 kJ per mole. This made Bartlett to think that if PtF6 can remove an electron from O2, it should be able to remove electron from xenon atom. He therefore predicted the reaction between xenon and platinum fluoride to form Xe positive, PtF6 negative. Xe plus PtF6 gives Xe positive, PtF6 negative. Bartlett carried out the reaction and found that gaseous xenon reacts with the red vapors PtF6 to give a yellow solid of composition Xe positive, PtF6 negative. This marked the first preparation of the compound of group 18, breaking the old myth that these elements are inert. Bartlett's this discovery opened a new field of chemistry, and within months scientists prepared fluorides of xenon, namely XeF2 and XeF4. Among the noble gases, xenon is known to form the maximum number of compounds, whereas krypton forms only a small number of compounds. Before we discuss the chemistry of noble gases, it is important to answer some curious questions, which are: what are the factors that are responsible for the late discovery of compounds of these gases? Why does xenon form the maximum number of compounds with fluorine and oxygen? Late discovery of noble gases. Before 1962, it was believed that noble gases were not reactive at all. This was attributed to the high first ionization potential and nearly zero electron affinity of these gases. All attempts to prepare the compounds of these gases were not met with success. It is interesting to note that William Ramsay, the discoverer of these gases, sent a sample of argon to the French chemist Henri Moissan, who discovered fluorine, to see whether argon reacts with fluorine. Moissan found that there was no reaction between fluorine and argon. This led Ramsay to conclude that noble gases are chemically inert. On the basis of chemical inertness of noble gases, Lewis in 1916 formulated the important rule. We today call it as the octet rule. According to the rule, when an atom forms a compound, it either gains, losses or shares electrons to obtain 8 electrons in its valence shell. You should remember that octet refers to a valence shell containing 8 electrons. Compounds of xenon. The historical reaction of xenon gas with platinum fluoride marks the first chemical compound of xenon. If you recall, Neil Bartlett discovered this reaction in the year 1962. Thus, xenon was credited the first and foremost element of the noble gases to open a new field of chemistry called the chemistry of noble gases. Today, we have a very rich, interesting chemistry of xenon compounds with highly electronegative elements or groups containing highly electronegative elements, in addition to some compounds of krypton. Of all the electronegative elements known, fluorine is the most electronegative. It is able to stabilize the highly oxidizing noble gas compounds. Now we are all set to discuss the chemistry and important properties of compounds of xenon in particular and noble gases in general. Xenon compounds. A. Xenon difluoride XeF2 preparation. It can be prepared by following methods. Number 1. Xenon difluoride is best prepared in the laboratory by heating xenon and fluorine in the molar ratio 2:1 at 400 degrees Celsius. Xenon is always taken in excess to avoid the formation of xenon tetrafluoride. XeF2 in presence of nickel at 400 degrees Celsius gives XeF2. Number 2. It can be prepared by subjecting a mixture of xenon and fluorine in the molar ratio 2:1 to electric discharge. Xe plus F2 electric discharge gives XeF2. Number 3. It can be prepared in quantitative yield by reacting xenon with oxygen monofluoride O2F2 at low temperature in a nickel or monal vessel. Xc plus O2 F2 at minus 80 degrees Celsius gives XeF2 plus O2. Properties. Xenon difluoride is a colorless crystalline solid which melts sharp at 129 degrees Celsius. Number 2. It dissolves completely in anhydrous hydrogen fluoride without any reaction. Number 3. It gets reduced to xenon with hydrogen. XeF2 plus H2 gives Xe plus 2HF. Number 4. It is soluble in water but undergoes slow hydrolysis to produce xenon gas. XeF2 plus H2 gives Xe plus O2 plus HF. Number 5. It gives substitution reaction with strong protonic acids HY. XeF2 plus HY gives FXEY and it gives XeY2, where Y is equal to OSO2F, OClO3, OSCF5, OOCCF3. Number 6. It reacts with sulfur trioxide to give xenon. XeF2 plus SO3 gives Xe plus S2O6F2. Number 7. Xenon difluoride is a very clean fluorinating agent. It fluorinates double bonds in organic compounds. XeF2 plus CH2 double bond CH2 gives CH2F plus Xe. Number 8. It is strong oxidizing agent. It reacts with iodine in the presence of fluorine ion acceptor to give IF. I2 plus XeF2 in presence of BF3 gives 2IF plus Xe. 9. It reacts with covalent pentafluorides such as antimony fluoride, arsenic fluorides to form two types of solid compounds in which xenon difluorides acts as a fluoride ion donor. For example, when the reaction is carried out in 1:1 molar ratio, a 1:1 compound is formed. XeF2 plus MF5 gives XeF2 MF5, where M is equals to P, AS or SB. These compounds XeF2 MF5 have been established to contain ionic species XeF positive and MF6 negative, where M is equals to P, AS or SB. Similarly, when the reaction is carried out in 1:2 molar ratio, a compound of composition XeF2 to MF5 is formed. XeF2 plus 2 SbF5 gives XeF positive and Sb2F11 negative. The compounds XeF2 to SbF5 has been shown to contain XeF plus and Sb2F11 negative ions. The ion XeF positive is strongly bonded to Sb2F11 negative through a fluorine bridging. Xenon difluoride has been shown to react in 2:1 molar ratio as 2 XeF2 plus AsF5 gives 2 XeF2 AsF5. The compound 2 XeF2 AS5 is conceptually equivalent to Xc2F3 positive AsF6 negative. The ion Xc2F3 positive has the expected linear geometry around xenon and an angular geometry at the central fluorine atom. Number 10. Xenon difluoride in anhydrous hydrogen fluoride reacts readily with platinum metal and sulfur powder and iridium to produce the highest fluorides according as Pt plus 3 XeF2 in presence of HF gives PtF6 plus 3 Xe. S8 plus 24 XeF2 in presence of HF gives 8 SF6 plus 24 Xe. 10 IR plus 5 XeF2 gives 10 IRF5 plus 5 Xe. Shape and structure of XeF2. On the basis of infrared and Raman spectroscopy, the geometry of xenon difluoride has been established to be linear. The geometry of XeF2 can also be explained on the basis of valence band theory. The valence shell electronic configuration of xenon in the group state is 5s to 5p6. Upon excitation, one of three 5p electrons is promoted to 5d orbital that results in two unpaired electrons, one in 5p and the other in 5d orbital. Now one 5s, 3 5p and one 5d orbitals hybridized to give 5sp3d1 hybridized orbitals that are directed to adopt trigonal bipyramidal geometry. The two orbitals which are singly occupied are used by two fluorine atoms to form two XeF bonds, whereas the other three orbitals can contain electron pairs. The two XeF bonds lie in a straight line while the three lone pairs of electrons occupy the equatorial position. Thus, xenon difluoride possesses the linear geometry as shown in figure 4.4. Xenon 4 compounds. Xenon tetrafluoride XCF4. Preparation. It can be conventionally prepared by heating a mixture of gaseous xenon and fluorine in the molar ratio 1:5 at 400 degrees Celsius under a pressure of 5 to 6 atmosphere. The reaction is ideally conducted in a nickel container. Xc plus 2F2 at 400 degrees Celsius 5 to 6 atm pressure gives XCF4. Xenon tetrafluoride can also be prepared cleanly by passing an electric discharge through a mixture of xenon and fluorine in the molar ratio 1:2 at low temperature and at low pressure. Properties. Number 1. It is a colorless crystalline solid with melting point 117 degrees Celsius. Number 2. It is quantitatively reduced by hydrogen gas. XCF4 plus 2H2 gives 4HF plus Xc. Number 3. It is a strong oxidizing agent. It oxidizes potassium iodide to iodine. XCF4 plus 4Ki gives 4Kf plus Xc plus 2I2. Number 4. It is a stronger fluorinating agent than xenon difluoride. It can fluorinate both elements and compounds. For example, XCF4 plus 2Hg gives 2HgF2 plus Xc. XgF4 plus Pt gives PtF4 plus Xc. XgF4 plus 2SF4 gives 2SF6 plus Xc. Number 5. It reacts with boron trichloride to form boron trifluoride. XCF4 plus BCl3 gives BF3 plus Xc plus Cl2. Number 6. It is readily hydrolyzed by water, giving xenon trioxide XCO3 as 6 XCF4 plus 12H2O gives 4Xc plus 2XCO3 plus 24HF plus 3O2. However, if the reaction is carried out at -80 degrees Celsius, it results in the formation of xenon oxyfluoride. XCF4 plus H2O on -80 degrees Celsius temperature gives XCOF2 plus 2HF. Number 7. It readily forms addition compounds with pentafluorides of phosphorus, arsenic and antimony of composition XCF2MF5 and XCF2-2MF5 where M is equals to P, AS or SB. XCF4 plus SBF5 gives XCF4 SBF5 which gives XCF3 positive, SBF6 negative. XCF4 plus 2 SBF5 gives XCF4 to SBF5 which gives XCF3 positive, Sb2F11 negative. XCF3 positive ions has T-shaped trigonal bipyramidal structure as shown below. Structure and bonding of XCF4. Spectroscopic studies have shown that XCF4 has a square planar structure. The valence bond description of XCF4 can be easily explained on the basis of electronic configuration of xenon atom. Xenon atom in the ground state has 5s2 5p6 in the outer electronic configuration. On excitation, 2 of the 5p electrons are promoted to 5d orbitals so that there are 4 unpaired electrons as shown in figure 4.5. A total of 6 orbitals, 1 5s3 5p and 2 5d intermix to give 6 sp3d2 hybridized orbitals. These orbitals are directed towards the corner of an octahedral. 4 of the hybrid orbitals containing single electron overlap with the 2p orbitals of fluorine to form 4 XCF sigma bonds. The other 2 positions are occupied by the lone pair as shown in figure 4.5. Xenon oxyfluoride XCOF2 preparation. Xenon oxyfluoride is prepared by the partial hydrolysis of xenon fluoride at -80 degrees Celsius. XCF4 plus H2O at -80 degrees Celsius gives XCOF2 plus 2HF. The structure of this molecule is T-shaped as shown below. The structure can also be explained on the basis of valence band theory. The outer ground state electronic configuration of xenon is 5s2 5p6. In order to account for the bonding, 2 of the 5p orbitals are promoted to the vacant 5d orbitals as shown in the figure. In this case, 5 orbitals, 1s3 5p and 1 5d intermix to give 5 sp3d1 hybridized orbitals. It is important to note one singly filled 5d orbitals is left unhybridized for pi bonding. 3 of the singly filled 5 hybrid orbitals overlap with 2 fluorine and 1 oxygen atom to form 3 sigma bonds with Two HCF and one XCO bond, one of the unhybridized 5d orbitals, is used in forming an additional bond with oxygen by sidewise overlap, that is a pi bond. Thus, in XCOF2, there is double bond between xenon and oxygen. In addition to two XCF single bonds, there are two lone pairs of electrons on xenon atom. Because of the presence of lone pair of electrons, there is mutual repulsion between the bonding and non-bonding pairs of electrons, and consequently there is distortion in the geometry. Thus, XCOF2 acquires a T-shaped structure as shown in figure. Xenon hexafluoride XCF6 preparation. It is best prepared by heating xenon gas with a large excess of fluorine in the ratio 1:20 at 300 degrees Celsius under 50 atmospheric pressure in a nickel vessel. Xc plus 3F2 at 300 degrees Celsius at 50 atm pressure gives XCF6. It can also be prepared by the reaction of XCF4 with O2F2 at low temperature. XCF4 plus O2F2 at minus 130 degrees Celsius gives XCF6 plus O2. Properties. Number 1. It is a colorless solid with melting point 49.5 degrees Celsius. Number 3. It reacts readily with water to form xenon trioxide, which is powerful explosive. XCF6 plus H2O gives XCO3 plus 6HF. Number 4. It is extremely reactive towards glass or quartz and produces the dangerously explosive xenon trioxide. This is the reason that the preparation of XCF6 is always carried out in a nickel vessel. Number 5. It reacts with pentafluorides of phosphorus, arsenic, antimony, and platinum and forms stable compounds. XCF6 plus MF5 gives XCF6 MF5, where M is equals to P, AS, SB or PT. The XCF5 positive in these compounds has been shown to have square pyramidal geometry as shown in figure 4.7. It reacts with alkali metal fluorides to form heptafluorozenates. Alkali metal fluorides are well-known fluoride ion donors. XCF6 plus MF gives M positive, XCF7 negative. On heating, heptafluorozenates decompose to give stable octafluorozenates as 2M. XCF7 gives on heating XCF6 plus 2M XCF8, where M is equals to RB or CS. XCFA2 negative has a square antiprismatic structure. Number 7. It is reduced to xenon upon reaction with hydrogen, ammonia and hydrogen chloride. XCF6 plus 3H2 gives Xc plus 6HF. XCF6 plus 8NH3 gives Xc plus 6NH4F plus N2. XCF6 plus 6HCl gives Xc plus 6HF plus 3Cl2. Shape and structure of XCF6. The valence bond description of XCF6 can be explained by considering the electronic configuration of xenon atom. The ground state outer electronic configuration of xenon is 5s to 5p6. On excitation, 3 of the 5p electrons are promoted to vacant 5d orbitals so that there are 6 unpaired electrons available, 3 in the 5p orbitals and 3 in 5d orbitals. Thus, a total of 7 orbitals, 1 5s, 3 5p and 3 5d orbitals hybridize to produce 7 sp3d3 hybrid orbitals. 6 of the singly occupied orbitals are used for bonding with 6 fluorine atoms. The 7th orbital contains a lone pair. The distribution of 7 hybrid orbitals should give a pentagonal bipyramidal geometry. As in case of IF7, however, XCF6 molecule has distorted octahedral structure. This can be explained if all the 6 positions are occupied by the fluorine atom and the lone pair is present at the center of one of the 6 triangular faces. This type of octahedron is called a capped octahedron, as shown in figure 4.8. Xenon oxytetrafluoride XCOF4 preparation. It can be prepared by the partial hydrolysis of xenon hexafluoride. XCF6 plus H2O gives XCOF4 plus 2HF. Number 2. It can also be prepared by the controlled reaction of xenon hexafluoride with silicon dioxide at low temperature. 2XCF6 plus SiO2 gives 2XCOF4 plus SiF4. Number 3. It can be conventionally prepared by heating a mixture of xenon and fluorine in the molar ratio 1:4 in presence of excess of oxygen. Xc plus O2 plus 4F2 at 230 degrees Celsius gives 2 moles of XCOF4. Properties. Number 1. It is a colorless compound with melting point -46 degrees Celsius. Number 2. It reacts with water and silica to form xenon dioxide with further reacts with hydrogen to give xenon trioxide. XCOF4 plus H2O gives XCO2F2 plus 2HF. XCO2F2 plus H2O gives XCO3 plus 2HF. 2XCOF4 plus SiO2 gives 2XCO2F2 plus SiF4. 2XCO2F2 plus SiO2 gives XCO3 plus 4HF. Number 3. It is reduced by hydrogen gas to form xenon. XCOF4 plus 3H2 gives Xc plus H2O plus 4HF. Structure and bonding. Xenon atom has the outer electronic configuration 5s5p6. In order to justify the bonding around xenon, in XCOF4, electrons sitting in p orbitals have to be promoted to vacant 3d orbitals as shown in figure 4.9. One 5s 3 5p and two 5d orbitals intermix to form 6sp3d2 hybrid orbitals which are directed towards the corner of an octahedral. One of the 5d orbitals remains unhybridized. In the formation of XCOF4, 5 of the singly filled hybrid orbitals of xenon overlap with the singly filled orbitals of 4 fluorine atom and 1 oxygen atom to form 4 XCF single bonds and 1 XCO single bond. The unhybridized 5d orbitals of xenon forms a pi bond with the oxygen atom. Thus the single XCO bond becomes Xc double bond O double bond and the molecule acquires a square pyramidal structure as shown in figure 4.9. Xenon dioxide difluoride, that is XCO2F2. It is prepared by mixing xenon trioxide with xenon oxytetrafluoride at low temperature. XCO3 plus XCOF4 at -78 degrees Celsius temperature gives 2 XCO2F2. It can also be prepared when xenon oxytetrafluoride is either hydrolyzed with water or made to react with silica. XCOF4 plus H2O gives XCO2F2 plus 2HF. 2 XCOF4 plus SiO2 gives 2 XCO2F2 plus SiF4. Properties. Number 1. It is a colorless solid. Number 2. It melts at 30.6 degrees Celsius. Number 3. It gets easily hydrolyzed with water to give xenon trioxide. XCO2F2 plus H2O gives XCO3 plus 2HF. Structure and bonding. The valence bond structure suggests trigonal bipyramidal geometry with one equatorial position occupied by a lone pair of electrons as shown in figure 4.10. The bonding can be explained as discussed in the case of xenon oxidifluoride. Xenon trioxide. XCO3 preparation. Xenon trioxide can be prepared by the complete hydrolysis of either xenon fluoride or xenon fluoride. 6XCF4 plus 12H2O gives 2 XCO3 plus 4Xc plus 24HF plus 3O2. XCF6 plus 3H2O gives XCO3 plus 6HF. During experiments on xenon hexafluoride, several explosions have occurred because of the hydrolysis of XCF6 to XCO3. The reaction can be controlled by carrying out the reaction at low temperature wherein the hydrolysis proceeds stepwise as XCF6 plus H2O gives XCOF4 plus 2HF. XCOF4 plus H2O gives XCO2F2 plus 2HF. XCO2F2 plus H2O gives XCO3 plus 2HF. Properties. Number 1. Xenon trioxide is a white, non-volatile solid. Number 2. It dissolves readily in water but explodes violently in the dry state. It is therefore advised to keep it in dissolved form. Number 3. It is not ionized in solution and concentration as high as 4m can be prepared. In alkaline solution, it behaves as a weak acid and exists as xenate ion HXCO4 negative. From HCO3 plus OH negative equilibrium exists HXCOF4 negative, which sodium salt can be precipitated as NaHXCOF4 1.5H2O. The aqueous xenate ion slowly disproportionates to perxenate and xenon gas. 2HXCO4 negative plus 2OH negatives gives HCO6 4 negative plus Hc plus O2 plus 2H2O. Number 5. It is one of the strongest oxidizing agent known in aqueous medium. In its oxidizing reactions, xenon trioxide releases xenon gas. HCO3 plus 6H positive plus 6 electron gives Hc plus 3H2O. It reacts with potassium iodide and liberates 3 moles of iodine per mole of xenon trioxide. HCO3 plus 6I negative plus 6H positive gives Hc plus 3I2 plus H2O. Number 6. It reacts with HCF6 and HCOF4 as HCO3 plus 2HCF6 gives 3HCOF4. HCO3 plus HCOF4 gives 2HCO2F2. Structure and shape of xenon trioxide. The outer electronic configuration of xenon is 5s2 5p6, which has no unpaired electrons. In the formation of xenon trioxide, it is anticipated to have 6 unpaired electrons on xenon atom. This could be accomplished by exciting 3 of the 5p electrons to the higher vacant 5d orbitals, as shown in figure 4.11. 1,5s and 3,5p hybridize to form 4sp3 hybrid orbitals, which are directed towards the 4 corners of tetrahedron. One can see that there are 3 electrons on xenon that remains unhybridized. 3 of the 4 hybridized orbitals, which are singly occupied, overlap with one of singly filled, the 2p orbitals of oxygen, and form 3 sigma bonds. The 3 unhybridized orbitals of xenon overlap sidewise with the 2p orbitals of the 3 oxygen and forms a double bond. It is important to note that one of the hybrid orbitals contain a lone pair of electrons. As a result, the molecule has a pyramidal geometry in place of tetrahedron as shown in figure 4.11. Xenon tetroxide, sodium perxenate NaHCO3 when treated with concentrated sulfuric acid gives xenon tetroxide HCO4. It is a yellow, volatile, highly unstable solid. It decomposes explosively in the solid state even at low temperature as minus 40 degrees Celsius. HCO4 gives Hc plus 2O2. Compounds of other noble gases. Of all the noble gases, it is the chemistry of xenon that has been studied in detail because of its reactivity towards highly electronegative element, namely fluorine. It is only recently that krypton and radon have been shown to react with fluorine to yield KrF2 krypton difluoride, KrF4 krypton tetrafluoride, and RaF2 radon difluoride. KrF2 deserves special mention. It can be prepared by reacting krypton with fluorine at low temperature in the presence of gamma rays. Kr plus F2 gives KrF2 at minus 193 degrees Celsius in presence of gamma rays. It is a colorless solid and get easily hydrolyzed. 2KrF2 plus 2H2O gives 2Kr plus O2 plus 4HF. It has been found to be a clean fluorinating agent. The structure of KrF2 has been shown to be linear, which can be easily explained on the basis of sp3d1 hybridization. RnF2 has been prepared, but it is highly unstable. No compound of helium and neon has been prepared so far. This is primarily because of their very high ionization potentials compared to xenon and krypton. In addition, there are no vacant d orbitals in helium and neon, where the s and p orbitals of these gases can be promoted favorably. Clathrate compounds. Clathrates are compounds in which atoms or molecules of one substance are trapped within the cavities of crystal lattice of other. It is important to note that rare gases were the first to be trapped and form clathrate compounds. Normal chemical compounds have ionic or covalent bond. However, in clathrates, atom or molecules of the appropriate size are trapped in the crystal lattice of other compounds. Although the gases are trapped, they do not form bonds. Clathrates are also known as cage or enclosure compounds. In these compounds, one of the most common has an open structure in the crystalline state containing holes or cavities in which the other component is trapped. Thus, if an aqueous solution of quinol 1,4-dihydroxybenzene is crystallized under a pressure of 10 to 40 atmosphere of argon, krypton or xenon, the gas becomes trapped in cavities of organic molecules. The crystal structure with cavities is called the host, and the gaseous atom entrapped in it is called the guest. The crystals are quite stable and can persist for several years without decomposition. However, when the clathrate is dissolved, the hydrogen bonded arrangement of beta-quinol breaks down and the noble gas escape. Even the clathrate decompose on heating with the escape of trapped noble gases. X-ray studies show that somewhat spherical cage of about 4 Armstrong diameter is formed by 3 quinol molecules being bound with hydrogen bonds as shown below. Thus, the ratio of quinol to entrapped atom is equally 3:1. The three gases Ar, Kr, and Xc all fit into the quinol structure. The argon compound has the approximate composition C6H6O2 whole thrice Ar. It is a stable crystalline solid with a very small organ pressure at room temperature. Helium and neon do not give clathrate compounds since their small size do not permit the inert gas to fit into the cage. Noble gases, with the exception of helium and neon, forms also clathrate compounds if water is crystallized slowly in the presence of noble gases. The maximum composition formula of such clathrates is NH2OMNG, where Ng is the noble gas. The value of N has been found to be 46, while that of M has been found to be 8. This ratio of 46:8 is very close to the experimental ratio of 8H2O:1 Ng. These clathrate compounds are commonly called the noble gas hydrates. The heavier noble gases have been trapped in the cavities of synthetic zeolites. Clathrate compounds find extensive uses in many applications. Some of these are: Number 1. The noble gases can be separated by forming the clathrates. If you recall, helium and neon do not form clathrates when quinol is crystallized from its solution in the presence of mixture of noble gases. This way, the heavier noble gases can be separated from helium and neon. Number 2. The most important use of the clathrate is that this provides a very convenient means of storing the radioactive isotopes of krypton and xenon produced in nuclear reactors. 85 krypton in the form of clathrate may be used as a source of energy for small atomic batteries. 85 krypton clathrate provides a convenient and useful source of beta radioactive. Clathrate compounds are convenient storage of inert gases. Thank you.